Thank you very much. Can you hear me? Good. Good morning, ladies and gentlemen. I'm here to talk to you about a fairly recent activity which has to do with the development of oil in non-conventional depth of water. Up to 500 meters of water depth, we consider that being conventional. Between 500 and 1,200 meters, we think it's deep water. And beyond 1,200 meters of water, we say it's ultra-deep water. These days, we are operating some gas and oil field, not a lot, but some, in 2,800 meters of water in the Gulf of Mexico. So there is a big difference there is a lot of challenges to be met between conventional production of oil offshore and deep and ultra-deep production of oil and gas at sea. So I'm going to present the deep water on a worldwide basis. Then I will just go through some main challenges of this activity, what we call the geohazard. Geohazard are all the problems associated with the bottom of the sea, with the geology. You will see that in deep water, the bottom of the sea does not behave like it does in shallower water or onshore. I'm going to talk about flow assurance. Flow assurance is the name to name the various methods which are utilized to ensure that the effluent produced by a well will reach the storage vessel on the surface. And I'm going to talk about various extreme conditions in which this activity is being handled these days. If I have time, I will mention to you two examples of deep water field, one being the Girasol field offshore Angola in an average of 1,500 meters of water, and the other one being the Canyon Express in the Gulf of Mexico in the US waters. So just a brief review of where, my slide is not very good, where you can find deep water activity. Gulf of Mexico, offshore Canada, Greenland, offshore Morocco, the west coast of Africa, which is very important, east coast of the South America. One very important area is Brazil in Campos Bay. And there are other areas like here, offshore the south of Australia. And I would say that every month a new discovery is made in very deep water throughout the world. So I used to work for the Total Oil company as a development engineer, and I just mentioned to you a few discoveries which have been made recently And for example, in Nigeria, in 99, 1,500 meters of water, we found Akpo. I was involved in this one. Then we found Egina, 1,500 meters, Moho in Congo, Bilondo in Congo as well, and a lot in Angola. The latest being Manjericão, it's Portuguese, in 2,000 meters of water. So far, we have developed Girasol, Dahlia, Lirio, and that's about it. They are in production. All the other reservoirs have not been yet, are not producing, but they are under study because there are no identical reservoirs. They are all different. So it's always a different case. And we have to spend a lot of time in studying the best way to develop each and every discovery. This is an idea of this activity in the north of the Gulf of Mexico. This is the coast of United States. New Orleans is here. All this white part is conventional production. All the blue area is deep water and ultra deep water. And all the dots are either production or exploration of hydrocarbon in deep water. Just our company was involved in Virgo, Matterhorn, Aconcagua, sorry. So that just to show you that this is a very recent industry, I would say about 15 years old, but there is already a lot of development. So to be able to develop, to produce gas and oil and gas in deep water, first of all, you need to be able to drill. So this is a graph showing since 1970 to the early 2000, the world records. So you can see 1970, when I started work, we were able to dip in 500 meters of water, and that was very, very difficult. These days, we can drill in more than 3,000 meters of water, but we don't use the same equipment. Drilling equipment utilized for drilling rigs, utilized for drilling in 3,000 meter equipment, 3,000 meters of water, are very big vessels. They are almost as big as an aircraft carrier. Because you can imagine that the weight of the equipment you have to handle is enormous. So you see this shape, quite very fast progress in the shape of the curve, show a very fast progress of the drilling capabilities. Production capacity were very much slower. In 1970, we could produce in 100 meters of water, whereas we were able to drill in 400 meters. And then in 1990, we were able to produce in 500, 600 meters, but it went very slow. All of a sudden, there was more interest, more money put in this new technology, and the capability of the industry became more important, and these days we can produce in 3,000 meters of water. That is, I would not say conventional, but that is achievable. So why do we go and try to find oil in deep water and ultra deep water? It's because you heard that the world is going to run out of oil, and we try to exploit oil everywhere we can. And it's not neglectable. The industry estimates that the reserve are 200 gigabarrels. That means 200 billion barrels, 200,000 barrels, 200 billion barrels. I would say these days the quantity of oil which is recoverable, conventional, is 1,000 billion barrels. So it's almost 20% reserve. Proven reserve is when you are sure that the reserves are there, that the oil is in the ground. You have been drilling, you have been making all sorts of studies. So far, it's only 65 billion barrels of oil, which is very interesting. I don't know the reserve of Mexico, but it should be in the order of magnitude. Okay, so the first challenge to be met by the industry is what we call the geohazard. So this is a slide showing some of the problem that can be encountered when you try to drill in the seabed, and you try to install equipment on the seabed. You will see later some pictures of some pictures of the equipment you have to put on the seabed, such as pipelines, manifold, wellhead platforms, stuff like that. So the first problem you can meet is diapirs. Diapir is a mountain of salt that crops up from the seabed like this, and quite quickly. If you don't know there is a diapir underneath, and you have installed a pipeline here, there will be a problem. So you better make a very good survey before you start locating your equipment. You have mudslides. The soil is not compacted, it's very unstable, and sometimes there are huge mudslides. And a mudslide like this can be 20, 30 kilometers long. You have mounds of carbonates. You can have pockmarks. I will explain to you what is a pockmark by showing you some seismic pictures. Pictures derived from the seismic. You have hydrates. Hydrates is a big problem. I don't know if you know what hydrate is. An hydrate is the result of the mixture of water and hydrocarbon gas, like methane. Under certain high pressure and low temperature, the water and the gas make some sort of ice. It looks like ice, and it's a very and it can block. For example, if you have that in a pipeline, you will block the pipeline. You can have a plug in the pipeline made out of hydrates in certain conditions. In deep water, you have water at 4 degrees temperature. On the seabed, everywhere in the world, the water is at 4 degrees. You have gas coming out from the sediment, and when the water and the gas meet, it makes hydrates. And it makes a hydrates layer just below the seabed. So you can also meet melt volcanoes. If your equipment is installed close to a melt volcano that erupts on the seabed like that, you are in trouble. So that's some of the problems that you have to take care of in deep water. This is a view. It's not a picture, because this is about 1,500 meters. Okay, so this is probably 20 kilometers by 10. So this is a top view of a seabed offshore Nigeria on Akpo field. And you can see, for example, here a number of faults, channels, a pockmark I will show you what a pockmark is. So if you have to install your equipment somewhere, if you have to drill, you better drill in this area, because all that is very unstable. What is a pockmark? This is a pockmark that we have taken from the previous picture. And this is a vertical cut. How do you saw that? This is a 2D seismic view of the soil in depth. You see here the layer of hydrate. Under the hydrate, you have gas trapped. And sometimes there is a leak of this gas. The gas leaks, that's what happened here. And when the gas reaches the surface, you have a pockmark. But you better don't be there. If you have your equipment in a pockmark like this, you might lose it. So before deciding what will be the shape of your development, you better have a very good preliminary soil survey. In this view, this is a seismic view. It shows you the area where there is hydrate under the seabed. All this yellow stuff is the area where there is hydrate. If you drill through the hydrate layer, you will immediately reach the gas trap underneath, and you will have an eruption. And your boat on the surface might be in trouble. A lot of boats, drilling boats, have been sinking because of gas eruption like this. So this is one other hazard associated with deep water. Okay, what do we do to develop these fields? How do we work in 1,500 meters of water? We cannot build a platform like this one. No, sorry, I will say. We cannot build conventional platform like you have in the Gulf of Mexico in 100 meters of water. It's too deep. So we use floaters. So this one is called a TLP, a tension leg platform, which is a floater, semi-submersible, with tethered, anchored on the seabed, under tension. This is one method. The other one is a spar. The spar is a floater which is moored on the seabed, and all the equipment, the drilling equipment, is installed on top of the spar. The advantage of this system is that in case of hurricanes, they can survive the hurricane easily because they are either semi-submersible or spar-type equipment. We use also FPSO. An FPSO that means floating, storage, process, and offloading. That's what we do on an FPSO. We have process unit. We have the wells going all the way to the riser with the wells going all the way to the surface. We store the oil in the hull of the vessel, and we can offload this oil into the export tanker. That's what we call an FPSO. These are two very special types of equipment, and I have no time to explain the details. So all these equipments, these floaters, the floating supports, they are linked to the subsea development by a number of piping, number of links that we call tiebacks. And there are two types of development. Development with the wellheads on the surface, we call that a dry wellhead, like this 4, and subsea wellhead subsea development. I will show you later an example of a huge subsea development. So, as you are civil engineers, I wanted to show you how we can moor on the seabed such big, huge floaters. So what we use is suction anchor. A suction anchor is a big cylinder, about 5 meter diameter, 10 meter high. The bottom of it is open, and the top of it is closed. So you just lower it down on the seabed, and it will penetrate the seabed by, I don't know, 1 meter maybe due to its weight. But that's not enough to install it as an anchor. What we do, we come with a remote operated vehicle, which is a remote control submarine. This submarine has a pump. It connects the pump to a pipe fitted on top of the suction anchor and start pumping the water out. So as soon as you start the pump, the pressure inside the caisson reduces, the pressure outside is still the same, and it creates a force, very important force, that drives the caisson all the way down to the seabed, into the seabed. And you have your mooring line going all the way to the surface, to the vessel that you want to moor. This is the mostly used in very deep water. The reason being that in deep water, the soil is always very soft and the caisson can penetrate easily. Okay, the next subject is flow assurance. This is a fixed platform, and not far away offshore you have an FPSO producing oil and gas in very deep water. This is a conventional fixed platform like what you have in the Gulf of Mexico, and the reservoirs are at the same depth. This is the reservoir. But this reservoir, this one, is much warmer than this one because the weight of the layer of soil here is higher. You have more sediment than here. So here the effluent goes out from the well at 80 to 90 degrees, whereas for the same depth of reservoir, in deep water it goes out at just 50 degrees C. So this is due to the fact that the density of the sediment here is much heavier than the density of the water. That's why the temperature here is lower in deep water. You will also see that here the distance that the pipe is running in the water is shorter than in deep water. And when the pipe is running on the seabed like this, the effluent in the pipe are going to be refrigerated. They are going to see the 4 degrees centigrade of the seabed, of the seabed temperature, and the effluent reaching the surface will be at a lower temperature than when they get out of the well. So if your effluent are colder, they become more, the viscosity of the effluents is increasing, and it's more difficult to extract this effluent. So what we normally do, I'm not going to explain in detail this scheme, but what we normally do is we install insulation on, this is a schematic showing the well, the flow line on the seabed, and the riser going all the way to the surface. So what we do, we install insulation on the sea line and on the riser to keep the product warm. And we don't do that normally in a conventional, at a conventional water depth. So what are the problems associated with flow assurance? One is in deep water. One with the hydrates. The hydrates, what do you do to prevent hydrate? Thermal insulation, heating, and we can circulate the oil in the system to avoid the temperature of oil to drop below a certain figure. We have wax deposition. So we use thermal insulation, we heat the lines, and we pick the line. We have a phenomenon which is called slugging. Slugging is when you have a mixture of gas and liquid in a pipeline, and all of a sudden you produce only gas, then you produce liquid, then you produce gas again, and this is very disrupting for the production. We call that slugging. So to avoid that, we use what we call the gas lift system, which has to do with injecting gas at the bottom of the riser. We produce sand, so we have sand control completion. In other words, in the wells, we install filters that prevent the gas, the sand, from being taken away by the effluents. And we have also well monitoring. We check the downhole pressure and temperature, and we test the wells. Another method is coming these days. You can see the FPSO, you can see the riser and the flow line going all the way to the wellhead. So in order to be able to circulate the oil from the well to the vessel at a very long distance, here we show distance between 10 and 25 kilometers. What we do is we install a multi-phase pump on the seabed, close to the wellhead. These pumps are able to increase the pressure of the effluent made of water, mud, oil, gas, all these things. So this is one possibility to ensure that the effluents will reach the FPSO. Another possibility is to separate the water on the seabed, here, next to the wellhead, and inject the water in the ground in order to reduce the flow of liquid in the line. You can imagine that to install this equipment in 2,000, 3,000 meters of water is quite a challenge. So these things are, this processing equipment are being developed these days. They are not fully operational. This is a slide showing various type of riser. What is a riser? The riser is a pipeline which goes from the seabed all the way to the various surface support. So we have the hybrid riser, where you have the riser is partly rigid, partly flexible. You have the steel catenary riser, where this part of steel catenary riser is this one. you compensate the heave of the vessel by the flexibility of the catenary of the riser. We have flexible hoses like this one. All this part is not moving, but all this part is moving up and down with the support vessel. This is an enlargement of the top of the hybrid riser, where you can see the rigid part of the riser and the flexible part going to the support vessel, to the FPSO. This shows you how the steel catenary riser are being insulated. You have the pipe itself surrounded by another pipe, and in the middle you have a gas. This is the best way to insulate a bundle of pipes, because the heat transfer between the gas is very low. This is a flexible riser. With this one has a number of small bore piping, where you have hot water going through, and that heat the riser over a considerable distance. So that's help preventing the heat loss of the effluent during its transfer across the slide of water. So this is a representation just to show you how big the equipment I'm talking about is. So this is the city of Houston, I think, yes? And this is a TLP, a spar buoy, which is anchored 1,200 meters above the seabed, with all the lines, the mooring lines, holding this platform in position, and these are the well risers. These are the pipes that bring to the surface the oil and the gas. So now I'm going to show you an example of a field which has been developed since discovered in 1997 and put in production in 2002, I think. So this is offshore Angola is here. This is offshore Angola, and the field is around 1,350 meters of water depth. So you have the reservoir of Girasol here. Next to it, we found another one, which is called Dahlia, which is now producing also. The third one, Rosa, Lirio. All these fields are producing these days. They are between 1,600 and 800 meters of water. Jasmine, that's all. So the reserve of the block, let's talk about Girasol. We have 700 million barrels of oil reserve just on this yellow spot here. Dahlia, we have almost 1 billion barrels. I'm not going to talk about this slide because it has to do with geology of the reservoir and or physical characteristic of the reservoir, and I don't think it's a good idea. What I'm going to tell you is that to produce this reservoir here, we had to install 23 production wells 14 water injection wells and 3 gas injection wells. We use water injection and gas injection to keep the pressure of the reservoir at a good level to allow the oil that we want to recover, to allow the oil to get back to the surface. So this is a view of the development. Between this point and this point, there are 35 kilometers. Between here and there, it's 6 kilometers. Water depth, 1,350 meters. Almost 3 kilometers away, we have a loading buoy that you can hardly see here. It's a buoy where the shuttle tanker, where the tanker come, they are moored to the buoy, and we export the oil through the tankers. You can see here 1, 2, 3 hybrid risers. The problems, water depth, marine currents. There are a lot of currents in this slide of water. High hydrostatic pressure. On the seabed, we have 150 bar pressure due to the seawater. Low temperature, 4 degrees centigrade. Formation of hydrate of wax. So we need thermal insulation, heating of all this network of pipe. All this, the equipment that you see on the seabed, we will go in a little bit more detail. They are installed in 1,300 meters of water, and if something gets wrong, you are in trouble. So they better be very reliable. And before installing a piece of equipment on the seabed, we run a lot of tests. And we make sure that the rate of failure of the equipment will be very low over a period of 20 or 30 years. Regarding the riser and the flow lines, we have a problem of mechanical behavior because this one, the vessel moves, heaves, goes like this, and the riser has to follow, and we have a lot of problem of fatigue. So the steel that we are using, the material that we are using must be very resistant to fatigue. And of course, to install all this equipment on the seabed means a lot of installation problem, means a lot of very big vessel to be able to install this equipment, very specialized vessel. So this is just a picture of a wellhead, a subsea wellhead. Here you have a man. This is the subsea wellhead, and these are 2 panels that can be operated with a remote operated submarine. So when you want to close a valve, for example, you have a handle in one of these holes here. So the submarine comes over, grab this red bar here with one manipulator, and with the other manipulator, he operates the valve. Okay? This has to be done when there is a problem with the valve. Normally, the valves are hydroelectrically operated, and they they can be remote controlled. But if there is a problem, you can do something with your submarine. This is the FPSO, the 3 risers. Then we have the production line coming to the bottom of the riser. We have injection lines. We have the 3 riser tower. We have flexible hoses between the top of the riser tower and the vessel. We have umbilicals. These umbilicals are utilized to control all the wellhead, the manifold, all the subsea equipment, which is electromechanically operated. And a 2 export line to the mooring buoy. So this gives you an idea of the rigid section of the riser. So you see the external diameter is 1.5 meters roughly. Inside there is a 22-inch pipeline. There is foam for insulating the various pipes. I told you that to prevent a problem with low temperature in the effluent, we have to insulate. So we use foam. Very special foam that can stand the external pressure. On this picture, you can see the 4 production line. You can see 4 gas lift line. There is 1 gas lift line per production line because we inject the gas in the production line to help the flow of effluents. We have 2 injection lines for water 8-inch. That's about it. This is a view of one element of the subsea bundle lying on the bottom. Again, you have 2 8-inch production lines. Why 2? Because we need to circulate the oil sometime in case of breakdown of one equipment. We want to circulate the oil in order to avoid blockage due to hydrate, for example. We have a service line. Sorry. So this line, we have, I think, more than 120 kilometers of these bundles. They were fabricated onshore in Angola in one piece, and they were towed on the seabed, dragged on the seabed with a tug, over a distance of about 400 kilometers between the yard where they were fabricated and the site, and then installed carefully in place close to the various pieces of equipment they should serve. This is a picture of the FPSO when it was built in Korea. It is very difficult. It's not possible to, at that time, it was not possible to build a bigger vessel than this one. It was the biggest vessel you could build in Korea, where we had the biggest, how do you call that? Shipyards. We have, this vessel is 300 meters long, 60 wide, and 30 meters deep. The dry dock in which it was built was 61 meters wide. So there was only half a meter spare on each side of the hull when we got the vessel out of the dry dock. This is another project. It's a project that we managed in the Gulf of Mexico. So we had to lay a pipeline that would drain three different fields belonging to various owners. But it was more economical to have one pipeline for 3 fields than one pipeline per field. So the 3 fields were Camden Peak, Aconcagua, and Camden Hill. So this is an artist's view of the area. You have the platform of Virgo, another platform named Neptune, a third one named Marlin, and Camden Hill here, Aconcagua not far away, and the last one Kings Peak. And the game was to link these 3 fields to Virgo with one pipeline. This is in 2,000 meters of water. So this is how the pipeline looked like. So just to show you what type of equipment we have on the seabed. This is the pipeline I was talking about. This is a manifold to which this well was connected, and the well was remote controlled through this umbilical and tether sledge, that was bringing all the fluids required to operate the valves, and that was providing all the informations for controlling the installation. As the three fields belong to different owners, it was necessary to meter, to get a measurement of the quantity of gas produced. So on each well, we had a gas metering system. Okay, I'm just going to give you a conclusion. Recent technical advances have allowed development beyond 2,000 meters of water. We are roughly at 3,000 meters of water. I don't think that we will go very much beyond that in the coming days. It's a challenge to make a deepwater project viable. Not only from the technical point of view, but from the cost point of view. These days, the price of development are jumping very high. And one of the reasons why I'm here is that I'm trying to convince young engineers like you to join this industry. In this industry, there are absolutely fascinating challenges to be met, but this industry is not very well known. So this presentation was to try to give you an incentive to come and join our deepwater industry. Thank you very much.
En este momento abrimos un espacio de 10 minutos para la sesión de preguntas y respuestas siguiendo la mecánica que se ha estado manejando desde el día de ayer.
Bueno, disculpe. ¿Sí? Mi pregunta era, cuando se termina un yacimiento, en teoría, y encuentran otro yacimiento con las mismas características, ¿se podría transportar el FPSO, en teoría? Gracias.
Yes, it's a very good question, but because an FPSO like the one I showed you cost us 5 years ago $1 billion. So a vessel like this, we can spare a lot of money but by reusing such a vessel and making some modification to cope with different type of effluents. You see what I mean? So in some cases we have sulfur in the crude oil. So in that case, we would have to add a module that would be able to treat this sulfur, but we install the module on this vessel and on the FPSO, and we can spare a lot of money. So this is a very good question.
Sí, quería preguntarle qué tan rápido puede bombear uno de estos barcos. ¿Qué tan rápido puede acabarse con uno de esos campos de petróleo?
How fast we can pump the reservoir. Generally, the principle is to pump the reservoir at a rate which will allow a production of roughly during 25 years. Okay? On these wells in very deep water, we have wells producing 30,000 barrels of oil per day. I don't know if you understand how big it is. Even in Saudi Arabia, where the reserves are huge onshore, I never heard about wells producing more than 6,000 barrels per day. The reason why we can produce so much is because the soil is very unconsolidated and the reservoir is fairly permeable. Okay? So the fluid can easily move inside the reservoir and go through the wellhead. Okay?
Disculpe, usted que lleva mucho tiempo en esto de yacimientos de petróleo y demás, ¿aproximadamente cuántos años quedarían de petróleo? O sea, ¿cuántos años puede haber que tengamos petróleo en abundancia?
Yes, that's a very good question. Again, when I was your age, one of my father knew was a friend of the guy responsible for the Institut Français du Pétrole, French petroleum industry. That was back in 1960. And my father asked this man, he said, my son is interested in going to the oil industry. What do you think? And the reply was, no, don't let him go into the oil industry. There is no more oil. And these days, we believe that at the current price of oil, which is $80 per barrel, which is enormous, we will start running out of oil. In other words, the oil production will decrease in between 20 and 30 years from now. Okay? At the price of 80. But if the price of oil reach 120, we can do much more. Maybe we can go deeper. Okay? And in that case, maybe in 50 years from now, we will still have oil. It's a question of price. Okay?
Excuse me. I would like to ask, how do you know if an oil reservoir is viable enough to make such a huge amount of inversion on it?
Yes, this is a big question for us. We have to make sure that the reservoir that have been found is technically, we can produce it technically, and we can produce it economically. Technically, there are sometimes reservoirs that we decide not to produce because it requires too many wells, or because there is high pressure of H2S, hydrogen sulfide, or because there is too much CO2, or because there is mercaptan or stuff like that. So technically, we don't produce them. But there might be some other reasons for not producing a discovered. For example, the reason can be economical. These days, for example, there is a shortage of equipment able to lay a pipeline in 200 meters of water, 2,000 meters of water. There are only 2 or 3. Imagine that you go to the contractor and you ask him, can you lay this pipeline for me? As he has no means, or all his means are busy, he will give you a very, very high price. Okay? And in that case, you will say, oh, forget about it. It's too expensive. Economically, the project is not viable. Okay? But we look in a lot of details to be sure that the oil is there in quantities, we have the right quantity, to make the project economical. And there, if you want, one of my colleagues can come to here one of these days and make a presentation of how we calculate the economy of a project, oil project. It's a very important subject. Offshore, of course, when the price of oil is jumping, then we have more chances to be able to develop the field. I remember in the North Sea a field called Alain. When we started back in 1986, when we started the project, at that time the price of oil was less than $10. Project was not economical. But our management said, we think that the price of oil will increase. So let's continue studying how we could develop this field. And this field is still producing, but these days it produces oil at $80. Different. It is very, very, very economical these days. But back in 1986, it was not at all. Not at all.